This is our sixth and final video for Chapter 4, talking about Newton's second law of motion. We have looked at these topics already and have reviewed what we already knew about free fall and looked at it again with respect to Newton's second law. Now we're going to look at the situation of non-free fall. So circumstances where it's something other than just gravity acting on the moving body. So we've dropped a bag of rocks off the ceiling, and to this point we have only looked at the force of gravity pulling it downwards, and we have ignored the fact that there is air resistance and drag working against it. Now we're going to start taking that into account. Something to think about is air more similar to outer space, or is it more similar to an ocean? And this makes a little bit more sense if you remember that air is a fluid like the ocean, like water. And if you haven't done this for a while, the next time that you are riding in the car, please don't do this when you're driving, but if you're riding in the car, stick your hand out the window. And once you get above maybe 30 miles an hour, you will definitely feel the air pushing against your hand. You can stretch your fingers out big, you can clamp your hand into a fist and feel the different air resistance. And the faster you go, the more dramatic you can feel that fluid against your hand. So this is what we're going to be looking at. And to a certain sense, this air resistance is related to friction, because it's also, in addition to that gross force pushing against it, you've got an atomic interaction between the two surfaces, and can have some things going on. So our object going downward experiences gravity pulling it downward. So the direction of that is down, and it also experiences, they're calling it drag. Drag gets a little bit complicated. There's some different things going on, but air resistance that is pushing it upwards. All right. Here's a couple conflicting negatives for you. We know this. Look at it this way. In the condition of free fall, we say air resistance is negligible. All right? When we are in the situation of non-free fall, then air resistance is not negligible. Air resistance comes into play in some circumstances. There are still plenty of circumstances that we can presume that air resistance is negligible, and your problems will point that out. What determines whether or not we can ignore air resistance is a couple things. One of them is the cross-section of the object that is falling. If you look straight up at an object, if you're directly underneath an object falling, and from that point of view what the surface area is, that's the total area that the object is pushing against the earth. If it is big enough, then there's enough going on for air resistance to take into account. The other thing that matters is the object's speed, and that influences whether or not, that influences the magnitude of air resistance that we see. And your object will no longer be in free fall when the air resistance becomes equivalent to gravity. So free fall, the object is accelerating with the force of gravity. If our object is falling at such a point that gravity is pulling it down and air resistance is pushing it back up, then we'll either be accelerating at a smaller value or we will no longer accelerate and we will be falling at a constant speed. So it's looking at it's comparing, we need to compare gravity to air resistance to see what change, how the motion of our falling body changes. When they are equal, no net force, no net force, no acceleration. Remember that when acceleration is 0, we still have a velocity, but when acceleration becomes 0, our velocity does not change. We can also call this our terminal velocity, our terminal speed, when we stop accelerating. What's the difference between terminal speed and terminal velocity? This is another review question. It's terminal velocity when there is a direction involved. And of course, we're talking about skydivers. When a skydiver jumps from a plane, he will accelerate due to gravity until such point as the air resistance pushing against his profile is equivalent to the force of gravity. And it isn't that he stops falling, but he stops accelerating. As the falling speed increases, air resistance builds up, our net force becomes 0, acceleration becomes less. When acceleration goes all the way to 0, that's when we call it a terminal velocity, a terminal speed. Here's an example for you. We've got a 20 Newton, we've got an object that weighs 20 newtons falling. So gravity is pulling it. And it is of such a surface area that it is of such a surface area and speed that air resistance is 5 newtons. What happens to the acceleration of the fall? All right. Remember that when we remember that one of the things that we gain from drawing our vectors is we put them relative sizes. So our downward force is bigger than our upward force. So what's going to happen to the acceleration of the fall? Is the acceleration less than g? And g is gravity of 10 meters per second squared. Does its falling acceleration become less than that? Does it become more than that? Does it stay? Does acceleration stay at 10 meters per second squared? Or is acceleration terminated so it becomes 0 and the ball falls at a constant velocity without any change in velocity? All right? Think about that for a minute. Here's a question. Are you in free fall? Well, we're only in free fall when we can assume that air resistance is negligible. And they tell us in this problem we have air resistance. So we are not in a free fall situation. So don't look at this one the same way you looked at problems in chapter 3. In this case, the air is pushing back up on the falling object. When we have our object, it's falling due to gravity, but it has air resistance pushing back against it. It will continue to accelerate, but the acceleration will be less than the acceleration due to gravity. Now, they work out for you that it will actually be falling at a rate of 7.5 meters per second squared. I invite you to pretend that you never saw this. That you never saw this part of it. That's a calculation that you get into when you take into account both air resistance and drag. That is around flying, and that's not an equation that you need to be committing to memory at this point in time. What you do need to commit to memory is that when it is a non-free fall, our acceleration is less than g. And g is the acceleration due to gravity, and it's our magic number of 10 meters per second squared. Okay? If it's a little bit confusing, the only thing that you need to lock onto right in this point in time is that this applies only to free fall. That number is what we remember when it's free fall and there is no air resistance. As soon as air resistance comes into the picture, the object doesn't get the full force of gravity because the air it's falling through is working against that. A 50 Newton person, hopefully with a parachute strapped to his back, is falling, and when he needs the condition at which he is going to have free fall is what? So here's your person falling, probably screaming, and the weight, the attraction between the mass of this person and the earth is 50 newtons. How much air resistance does this person need to reach a terminal velocity, to stop accelerating? Remember, terminal velocity means that acceleration equals 0. So does he need to be at a point where the air resistance is less than 50 newtons, exactly 50 newtons, or more than 50 newtons? Or do we not know? Is it something different? All right. What does the condition, think about your free body diagram, what does the relationship between these two forces need to be so that our skydiver stops accelerating? Skydiver needs to have the air resistance pushing him up at the same magnitude of force as gravity is pulling him down. And that is the definition of terminal speed. We are at terminal speed when the summation of forces equals 0, and that makes acceleration be 0. As the skydiver is falling faster and faster through the air, what's happening to the air resistance? The force between the skydiver and ground is due to the massiveness of the person and the force and the 10 meters per second squared that is gravity. As the skydiver is falling, what's happening to the air resistance? Does the air resistance increase the faster the skydiver falls? Does air resistance decrease? Does air resistance stay the same? Or do we not know? Don't try this experiment at home. As the skydiver is falling in faster and faster, the air resistance increases. So we've looked at our skydiver, and as she continues to fall, as she's going faster and faster, and air resistance becomes a factor, the net force downward decreases. If that's the case, what is going to happen with her acceleration? She is falling downward, her velocity is increasing. We cannot ignore air resistance. So what happens with her acceleration as she continues to go faster and faster? Does her acceleration increase? Does it decrease? Does it remain the same as if she were in free fall? Or do we not know? There's your question. Well, her acceleration decreases. The net force decreases. She is still falling, and she is still increasing in velocity, but her rate of increase is changing. Maybe a little bit different than your first question your first response to this question would have been. All right, two people are jumping together at the same time. One is more massive than the other person, and they have the same size parachutes. Who's going to reach the ground first? This is going to take a little bit more complicated thinking. We've got somebody more massive, we've got somebody less massive, and everything else is the same. Who is going to reach the ground first? The lighter person? The heavier person? Do they both reach it at the same time? Is there not enough information? Okay. If we were able to ignore air resistance, then this would be the same problem as dropping a bowling ball and a golf ball from the roof at the same time. However, we can't do that. We've got air resistance. What else do we need to know? How would we go about looking at this? In this case, the heavier person reaches the ground first. They both have the same, at a given speed, they both have the same drag force, but the heavier person is going to have a greater downward force. In other words, the heavier one is going to drop further before he or she reaches terminal velocity. The less massive person is going to reach terminal velocity first. So imagine that you are holding both a coin and a feather at the same height, and predict what happens when you let go of both of them at the same time. And this is what everybody always gets confused about with Newton's first law. You know, the idea that if I have this coin and the feather at the top of the building, you know, you don't believe me when I tell you that they would fall at the same rate. And they don't, because the feather has a very large surface area and a relatively small mass, so it is going to reach its terminal velocity right away, and floats to the bottom with no more change in its velocity. The coin, on the other hand, the air resistance is negligible. It's got a larger mass and a smaller surface area, and it does not reach a terminal velocity. So it continues to increase its speed because of the acceleration due to gravity and no counteracting forces. All right. I hope that you've all seen this demonstration. If you draw a vacuum and drop the coin and the feather at the same time, I will load a video of this happening for real, because your eyeballs see it and your brain doesn't accept it, because we know how feathers work. But if there is a vacuum drawn and there is no air resistance, well, what is it that you see? And when there's no air resistance, the coin and the feather fall at the same rate of increasing velocity. They have the same acceleration and no counteracting force. So they both fall with the acceleration due to gravity. I'll find you a video so that you can see this for real. So when the coin and the feather are falling in a vacuum, there's no air. There's no air resistance, and